Good evening. I'd like to talk about the topic of entanglement. And lots of people have a little difficulty with entanglement. I don't think it's so super hard to understand once you understand a little bit of the nature of nature. Well, the basic nature of nature is that it's wavy, always, everywhere, always. I mean, the physical part and what we can see and observe and touch, etc. Nature is wavy in its nature, and a lumpy wavy, in a lumpy way, and in wave particles, except apparently. And you could represent it like, well, something like this. You can see it. It's wait. Like this. You can see it better altogether. It's a wave particles. Nature is constructed with apparently wave particles, and not only the ones that we are studying, but also your body, your instruments, the measurement instruments, consist of a lot of wave particles, actually atoms, electrons, photons, whatever kind of ions, whatever's going on, it's wavy. Wave packages. That's why we have wave functions. This we got to really understand and grasp that and Einstein showed it, Max Planck showed it, Niels Bohr accepted it and worked with it, and so on, so on, so on, so on. De Broglie wavelength and so on. He used it, he found it out. So we have to accept that nature is lumpy, wavy in nature itself, like wave packages. That's the essence of how nature is constructed. And as you know, I'm a messianic believer, in a Jewish way, Jewish messianic believer. So we have to accept that, at least I accept, that God has created it in such a way that it's a lumpy, wavy in nature. But that has some consequences, seriously consequences, especially for how we deal with that's how we came up with quantum mechanics, but also quantum entanglement. And if a particle such as this, a wave particle, I hope you can see it well, a wave particle is splitting in two, then what happens is basically this. You have all of a sudden two wave functions, and in the middle here, it's connected. This is the particle mainly, but it's still connected, even though it is very vaguely or less in between the particles. It's still connected with each other. And this makes that particles are entangled. I mean, a wave particle is actually a fluctuation. It's constantly fluctuating. But now it splits into two separate particles. Always, suppose you take the spin as a study, a subject to study. It's always the opposite of the other one. Whether it's charge, whether it's a spin, it's always, at first it was one particle waving at something, and then it becomes two particles, but always opposite, because the conservation laws, law of conservation of energy, law of conservation of charge, law of conservation of spin, etc. So it always is opposite waving, but they are still connected due to its wave function. It is, you can describe it with a wave, and that means that it's still connected, even though the connection may be very faint, but it's still connected, and they are always opposite, but moving. I mean, the spin could be changing, alternating very rapidly, but it's still always opposite and that's not what we perceive. We perceive it only if we measure it. So even then, if particles are separated very far away from each other, like this, in this situation, yeah, and if the distance is very big, even though it doesn't matter how big the distance is, they are still connected via this waviness. It's particles are naturally non-local. Of course, we observe the local thing, but it's trembling. Space is not silent. Space always trembles and shifts and moves and twists and vibrates. And so space is very vibrant. So and this waviness is transported over large distances of space. So if you would put a graph of the spin, for example, the spin, at this particle constantly, suppose that you would be able to constantly measure it, it was constantly fluctuating, just like that. But that means that the opposite part, the other particle, is actually fluctuating with its spin in the opposite direction, always, and it's connected via, again, this connection, because of the law of conservation. But they are always opposing. If this spin is up, then this spin is down, etc. So, but it's constantly changing, constantly. If this goes up, this stays here for a while, then this stays there, there, and there, and waving, and there. But always until the moment that we are measuring it. Because if you're measuring it, then this particle may be certain because you measured it. But that means automatically that this particle is also certain because they're linked together. It's like waves are always. It's like with a string of a guitar. I play guitar, as you know, and if you, it's like a standing wave. Suppose that you have one string and it's going like this, but so all of a sudden you split it. Well, it's the same thing, but the things are opposite. You get the upper tune, the first. Upper tune is the bass tune. If this is the string, it's waving. But then again, it splits. You have an overtone or whatever. But it's always opposite. Also with the guitar, and so on. Well, so this is how they stay connected. They are connected, but always opposite, because that's the nature of nature. And it doesn't matter how far you draw them apart. That doesn't matter because they're still fluctuating. Starting from the beginning, and they were always fluctuating opposites until you measure one. Then you also automatically have the other one measured, and then you know it. So that's why entanglement is actually a fundamental thing from the waviness, the lumpy waviness of nature, and that goes for all particles. I mean, it's not too hard to comprehend. I mean, but you have to accept that everything is wavy, and that's what I want to share with you, folks. And also, your measuring instrument is wavy. It consists of wave functions. So you can, if a particle hits a screen, then it's merging with the wave functions of that screen or of your detector. So it's merging wave functions. We have to start thinking in lumpy waviness of nature and in wave functions, and deal with that. That's what I want to share with you. Okay, thanks for watching. Hasta la basta. See you next time.